So first, I would like to thank my advisor, Predrag Vasilevich, for all his suggestions and advices, not only on this research, so I do appreciate that. And also I would like to thank my committee members, Dr. Yes, Dr. Greenstein, and Dr. Hamovich, for their valuable discussions to improve the quality of our research. And I would like to thank everybody here giving me this chance to introduce our research and defend my thesis. So my thesis title is Sequence Design with Applications to Ultra-Wideband Communication Systems. So first, backgrounds and some motivations. So our sequence design highly related to the ultra-wideband system. So I will talk both of them. Then we have 3 topics today. The first topic is complementary sets related ultra-wideband system. The second topic is orthogonal variable spreading factor codes with a zero correlation zone. That's a special kind of sequence, and we apply them to the quasi-synchronous direct sequence UWB system. So I will also discuss all the issues there. The third topic is ternary multipath beamforming sequence. So at the end, I will conclude and show the future work. So for the background and motivations, I will talk both UWB and the sequence, like their definitions and like what motivates us to look at the sequence, particular sequence design. So ultra-wideband system is defined as any radio technology as long as you have a bandwidth more than 500 megahertz, or you have a fractional bandwidth more than 20%. So this kind of technology is a candidate for the high-speed 5-layer enhancement to IEEE 802.15.3, which is a wireless personal area network. So we may want to use ultra-wideband technology to transmit image or multimedia. So that means this is a high-speed applications, and also is no cost, no power applications. So
just an update.
Okay.
The committee does not exist.
Yeah. So now actually they give up to merge their 2 proposals. Let the market decide what's going on. So but basically ultra-wideband system can operate in this huge bandwidth.
Do you think someday one of those definitions will laugh at?
Which one?
I'm asking.
Yeah, you can be this or you can be this.
No, I mean it's like if in 30 years from now, somebody reading this thesis will say, "Oh, look, they have this very funny definition of
This one, right?
wideband."
Oh,
no, I think it's more likely the
500?
500 is just a number that has nothing to do with. Do you think it has something to do with technology today, or is it that it has to do with the fact that maybe line of sight is up to 10 gigahertz, so it'll always be. I mean, if somebody was working on ultra-wideband in the 1950s,
Yeah.
they might say, well, it's anything wider than 500 kilohertz, right? Or
Yeah, this.
50 megahertz.
I guess he's saying maybe in some years that this is going to be a narrow band.
Well, I might say maybe not. Maybe I'm saying maybe actually this is really a number that reflects like a line of sight is really 10 gigahertz, and so 500 megahertz is always going to be a really kind of you'll only use 500 megahertz if you're doing a thing like the current UWB where you plan on overlaying.
So the question,
a lot of existing applications.
The question may be, like if I give you a 10 kilohertz bandwidth load, from 400 kilohertz, is that as valuable as 10 megahertz at 10 gigahertz, right?
Yeah.
So at the very beginning, people use this this fractional bandwidth to define UWB. But later the IEEE group, they think, well, just use 500 megahertz, that may be easy. But this means if you want to design any ultra-wideband system, you have to have the instantaneous bandwidth that cover this 500 megahertz. You have to do that.
He's asking about future D. He's not asking about current.
Yes.
He understands. We understand the definition.
Okay.
But he's asking whether maybe 500 megahertz in some future is not going to be ultra wideband. Maybe it's just going to be.
Yeah, that always.
It'll be ultra wideband by definition, and the higher bandwidth systems are called super wideband.
Oh,
They keep escalating
Exactly.
Right.
Oh, okay.
It just won't be seen as the ultimate anymore. This isn't ultimate wideband, it's only ultra wideband.
Okay. So because it has a huge bandwidth, so compared to the narrowband, then because you transmit something contain huge bandwidth, so which really increase the ability of the receiver to resolve the multipath component. Here I list some channel experiment results. So this is the number of multipaths which contain 85% of the overall multipath energy. So this is typical ultra-wideband indoor channel. So if for the 9 offsets from 0 to 4 meters, then basically you will have 24 multipath components in average. And if it's a non-9 offset, then you will have more multipath components. So for the ultra-wideband system, the challenge is how you can connect all those multipath energy to improve your system performance. So for the direct sequence UWB, actually in the proposal, they propose to use 16 fingers rake receiver. So that really make the receiver complex because you need more fingers compared to narrow. You need more fingers to connect the multipath energy. So because ultra-wideband system is also a no-cost design, so we don't want to introduce complexity in receiver side. So we look at this problem at the transmit side. And what we really do is consider the sequence design. So we try to design the sequence. If the sequence is good, so let's say we keep the complexity of the receiver at the same level, then if you use our sequence, then you have improved system performance. However, if you want to keep the performance the same, then use our sequence may lower your receiver complexity. I will show you later that if you use one of our sequence, then you simply use a correlated receiver, then you can achieve the same thing as the MRC rake receiver if you use a common sequence. For the ultra-wideband, it's also high-speed applications. So which means for the direct sequence-based UWB, you have to transmit the sequence with short length so that you can at fixed time interval you can send more symbols. But the problem is in this dense multipath environment, then you may suffer from severe inter-symbol interference. So the challenge for the sequence design, how you design sequence really have good correlation property to suppress those interference. Okay.
Are those the number of multipaths you have in those 3 categories?
Mm-hmm.
So what does it mean to have 36.1 or 61.5?
Oh, because this is in average. They do a lot of different channels and they do different.
Okay, so
yeah.
These are just percentile levels. If you plot the CDF of the number of multipaths over many numbers.
Yeah.
Okay,
so that's why not the integer here. So we do want to construct sequence with good correlation properties. So now let me introduce what's the sequence. So in our research, we define sequence as a discrete time complex value signal in which the order of its element is well defined and significant. So this is a typical expression for a sequence. All these are its elements. So let's say if we have n elements, then we say the length of the sequence is n, or we say the period of the sequence is n. So for sequence, why the order of the elements is significant, important, because that order determines the correlation function of the sequence. When we play with sequence, the first thing that we look at is the correlation function of the sequence, because that's have particular importance for the communication system. So here, first thing is the autocorrelation function. So in this autocorrelation function, which means you have the same sequence, you correlate the sequence with its shift copy. So this one is a periodic autocorrelation function, which means you have a sequence, you have a shift copy. You just do the inner product of this common part. Then that gives you the periodic autocorrelation with the shift L. So this is a periodic autocorrelation function. Another one is a periodical one. Because in the communication system, we use this sequence to carry the information bit. We periodically transmit the sequence. So sometimes people look at the periodic autocorrelation like this. You always periodically extend the sequence and do the inner product with the whole sequence length. So this is a periodical one. But one thing is, if you know the periodic autocorrelation, you can always get the periodical one. So sometimes people say a periodic autocorrelation may have more importance than the periodic correlation. So in our research, we mainly look at a periodical one. For the cross correlation, which is the same thing as the autocorrelation, but the difference is you have two different sequences involved. So sequences find a lot of applications in the communication system. For example, we know this is something called box sequence. So this sequence, if you look at it, is a periodic autocorrelation. All its side lobes strictly less or equal to 1. So this means you transmit this sequence, and at the receiver, you use a correlator receiver. So any multipath signals correlate with your the sequence at the receiver, then that one actually is the side lobes here. So if you can keep all these side lobes low, small, then you can suppress the multipath interference. We know that the box sequence actually used in the IEEE 802.11b for the 1 or 2 megabits per second that data rate applications. So another good sequence, maybe another example for a good sequence is M sequence. This one has, if you look at the periodic autocorrelation, all the side lobes strictly to be -1. So this sequence has widespread applications, like for the typical CDMA system, they may use long-length M sequence. So for the cross correlation, that means for a CDMA system, you transmit, you assign different sequences to different users, and you may have the multiple access interference. So if the sequence has good cross correlation, which can suppress the multiple access interference. So all in all, we want to design the sequence with this kind of ideal correlation properties. So look at its autocorrelation, all the side lobes to be 0. And you pick up any two sequence, the cross correlation, all the values for the cross correlations to be 0. So this is our ideal case. But that ideal correlation cannot achieved by the binary sequence, or we say by a non-trivial binary sequence. So that's why somehow we look at the ternary sequence. For example, this is the EPA12 perfect ternary sequence. If you look at the periodic autocorrelation of this sequence, then all the side lobes to be 0. So ternary sequence, which we insert some 0 element into the sequence, which really increase the correlation, improve the correlation properties. So that's why we look at ternary sequence. And another thing is ternary sequence is very good for the direct sequence ultra-wideband impulse system, because this 0 elements is kind of like you turn off the power of the transmit. So actually for the 802.15.3a, the proposal for the direct sequence UWB, they also use ternary sequence as the spreading sequence. So this is our motivation that why we use ternary sequence. And also in our research, if our series or our construction method can extend from ternary sequence to non-ternary sequence, we will always go that far to make our research general. So we may also look at complex value sequence.
I think we started the research before the proposal.
Yeah. So another way to classify sequence is traditional one-dimensional sequence and a sequence array. That we have several sequences. We call this is a two-dimensional sequence. So in our research, we look at both of them. So for one-dimensional sequence, if you look at the aperiodic correlation, then basically you cannot achieve ideal aperiodic correlation. So that's why we compromise that ideal thing. We just make some zero correlation zone to suppress the multipath interference. Or in a synchronized system, you may have some synchronization errors. So if you look at this zero correlation zone in the cross correlation functions, that may somehow bear some synchronization errors. For the two-dimensional sequence, the good thing is it can achieve ideal correlation properties.
What is the correlation for these two-dimensional?
Yes. Yes. For the two-dimensional sequence, the correlation function actually is the sum of the correlation function of them. Yeah, I have slides later. That's our first topic.
Maybe you can jump.
Oh, okay. Actually, it's here. So our first topic is two-dimensional sequence, which is complementary sets. This is a two-dimensional sequence with ideal correlation property. So I will introduce this kind of sequence and how to construct them, how to apply them to the orthogonal-pulse-based UWB system, how to solve the peak-to-average power ratio issues. So for the two-dimensional sequence, the correlation actually is you do the correlation of each row sequence and you sum them, then that's the correlation function for the two-dimensional sequence. So here, if it is a complementary set, then if you look at it as correlation, aperiodic autocorrelation, then that's the ideal case. And if only two sequences in this set, then this complementary set is reduced to complementary pair. You have only two sequences.
So if there's I understand. So if there's two sequences,
yes,
talk about the aperiodic.
Aperiodic.
It looks like this.
Yes, you sum the aperiodic autocorrelation function of this and this, then it will be this. For this sequence, you have aperiodic autocorrelation functions. For this sequence, you also have one. Then you sum them, then you get this. Yeah.
So he defines the autocorrelation for a 2D sequence as a sum of the autocorrelation of each row. That's all.
Yeah.
And
so
you call this 2D sequence is what I was sort of reading the thesis thinking of as a pair of sequences. You're calling a 2D sequence.
Oh, 2D actually is two-dimensional. So like typically in communication system, for this row sequence, actually that's a time direction.
Yeah.
You send the chip, right? For this, basically you may have orthogonal channels, or you like OFDM or whatever. So that's another dimension. So you have to transmit the whole thing, so on two dimensions. But for the typical one-dimensional sequence like this, basically you just have time dimension.
So,
I have to reread everything.
so
Go ahead, Larry. I'll
Okay.
jump in.
I just want to follow up on that. So in the two-dimensional case, you're either sending it on two orthogonal frequencies or two orthogonal polarizations.
Yeah.
But, okay, simultaneously in time.
Right.
Did you think how to do it for the UWB?
Yes, I will show that how to apply them to UWB system.
So I was thinking about almost everything I read, right, in the context of sort of like multi-code CDMA kind of situations, where you
Yes.
are looking at the sequence properties of the set,
Yes,
right?
yes.
Sequences, and it seemed like all your definitions were good, right? You want sort of low sort of correlations
Right.
in various ways.
Right.
I didn't realize somehow in reading the thesis that you were really thinking about this kind of a multi-dimensional sequences that are both time and frequency. Like somehow that really escaped me. And I'm
Okay,
thinking
yeah,
actually
maybe I should
now
emphasize that, yeah.
It's like I almost have to start over because in many places in the thesis I found I started off thinking, well, wait, somehow my impression was that the sequences in one of these matrices were the columns. And then I'd be reading and you do some operations that was like, no, and then I concluded, all your sequences are really the rows, right?
Oh, because
Later I will talk about the column.
Because he cares about the properties of columns.
Later I will talk about the column, yeah.
So-
But now,
So
yeah.
anyway,
yeah.
maybe
so when you write, for instance, like sort of a notational thing, when you write a bold-faced little a or a bold-faced small c, right? That's a vector, right?
Yeah, this is, yeah.
No, that's a matrix.
This is a matrix, this is the element.
One up at the top,
Yeah, this is the vector.
which is, and it's always a row vector.
It's always a row. It's not always a row vector. It's a sequence. Yeah, sometimes it may be like.
No. This is like that. It's like you're torturing your readers.
Okay.
Like if in the thesis, right? Every time you write a bold-faced lowercase letter, make it always be a row or always be a column. And then if you want columns, if you do it all as rows, then use transposes for columns or something. But it becomes very difficult, right? If your definition of a vector is sometimes a row or sometimes a column.
Okay.
Like the symbol notation. Like you want the symbol to be able to signify which one it is. So when you want columns, if you want these to be rows, then put transposes on all your columns to help poor readers like me.
Okay.
I don't
Okay.
know if it for him matters.
Yeah, actually,
It really doesn't matter to him, but
No, but I
Yeah,
mean, like even here, I don't think it matters.
you don't think. Actually, the sequence may not be a vector, so it's just a sequence.
No,
It
but
can be a row,
I
it can be
think
column.
all of them you
Same.
can define as vectors and everything is the same. There's no notion of.
no, but he does all of these concatenations of, it's this, and now he calls that something called capital C. And
But when he
sometimes-
does concatenations, it's always a column, so it's a vector column.
Oh, no, I think he many times is concatenating rows on top of each other or columns next
No,
to each
if
other.
it's a row sequence, the concatenation is just the concatenate row sequence. If it's column, then concatenate the column. Yeah, that's
Well, but that's sort of the
Okay.
opposite of, there are many other people who like the way they use signal processing is when they start concatenating vectors, they create super long vectors, right? There's, been you've all
Okay.
been involved in somebody's thesis where super long vectors was the notational solution, right? I think if
okay.
it really helped.
You're probably correct.
All I can say is if you did that, you'd have one reader who was less confused by notation.
So here we talk about the autocorrelation of this complementary set. So here we define the mate, which means you have two complementary sets. And you do the cross correlation of the corresponding row sequences. And then you sum them. Then for the complementary, if this complementary set is the mate of the other one, then the cross correlation will be ideal correlation. So we also define mutually orthogonal complementary set. So this is a set of complementary sets, and any one of them is a complementary set, and any two of them are mates of each other. So this is a small example, shows how we apply complementary sets in orthogonal channel communication system. So let's say C1 and C2 is a complementary pair, and the same information bit will be carried by both of them. So C1 and C2 will spread this information bit, and you sum them, you transmit out. So these two channels, let's say, is orthogonal. Because this is a multipath channel, so this is the, let's say, the line of sight. This is a delay version. So in the received signal, you may contain this one and the delay copy. So at the receiver, we know both sequences, and we do the correlator to the whole thing. Let's say the green one correlates with red one because the channel are orthogonal, that always cancelled. So this one correlates with this one. Actually, it's the autocorrelation of C1 with the time delay L. So this red one correlates with this red one. Also, it's the autocorrelation of C2 with delay L. Based on the complementarity of the complementary pair, this should be 0. So which means the multipath interference has been cancelled. So complementary sets has a long history. In 1961, Golay, so just now I show you complementary pair. Actually, first look at by Golay in 1949 or 1961. So that has a long history. And then later, Cheng and New extended to the complementary sets. Not only two sequences in the set, but more. And later, people look at complex valued complementary sets and multi-level, and somebody look at the ternary complementary pair. So for the complex valued complementary sequence, actually, it also has its application in 802.11b for the high data rate, like 5 and 11 megahertz. They use complementary code king scheme to do the spreading. So that's the complementary sets. And in 2000, Cheng and Bell, they apply those kind of things to the asynchronous multi-carrier direct sequence CDMA system. So we look at this ternary complementary sets to ultra-wideband system, and we also try to solve some peak-to-edge power ratio problem.
So all people who talk about complex valued sequences are talking about using +1 - 1 plus j minus j.
Yeah, that's sometimes people look at
That's the Q. So
for the complex value. So basically, this means two things. One thing is you may have a constant amplitude and you have a different phase, and also you may have different amplitude. So both of them are complex value sequence.
So the phase doesn't have to be pi over.
Not necessary. Yeah. Okay. But for the just now I said an example which is 802.11b. In that case, that's like 1 - 1 j minus j.
What about your ternary sequences? I mean, if you think of them as not complex, then they're just bipolar or zero.
Right.
But don't you, when you talk about complex ternary sequences, what does that mean?
No, I didn't. I just say binary sequence. So
But earlier you said sequences being complex in general.
Everything actually are.
That one, right?
Yeah.
Oh, okay.
Yeah.
So he's into
Yeah.
the non.
So your ternary sequences don't have phase in them.
Don't have, yeah.
Except in the sense of 0 and pi.
Yes,
Okay.
yes.
His focus is on that, but some of his results are more general.
Yeah. So our focus actually is like this.
He looks at PAPR, that could be some of the results are more general than.
So one thing for the complementary sets is people can find some construction way to design the complementary sets. So that's good because in sequence research, people either do the exhaustive search to find the good sequence or do the construction way. But for this one, since you have some construction method, so which can easily design the complementary sets to different size. So, but for that design, all the design actually started from the complementary pair. Just now I said only 2 sequences. So one thing I want to emphasize is for the binary complementary pair, it only exists with the length in this form. So that means you cannot find the binary complementary pair with arbitrary sequence length. But for the ternary sequence, you can. I just show you something from from 2 to 12. But actually, you can find ternary complementary pair with any length. So which means, based on the construction method, from this ternary complementary pair, you can construct the complementary sets with much more flexibility in the sequence length, in the complementary set size. So that gives you more flexibility in choosing the sequence length. So that's the advantage of ternary sequence. Well, so we apply complementary sequence in the ultra-wideband system. So let's say this is a multi-channel transmit. We have M orthogonal channels. Each channel may have a orthogonal pulse, like psi 1, psi 2, or psi m. So the same information bits will be spread on all the channels, and you sum them. So this actually is a pulse trend. You have a complementary set. So this row sequence will be the spreading sequence in this channel, and this row will be something in this channel. So you sum them and transmit out. At the receiver side, you have the same copy of those complementary sequence. You do the correlation and you detect. Just now I show a simple example which shows that the multipath interference will be cancelled. And actually, for the multiple access interference, if you assign mutually orthogonal complementary sets, you can also cancel the multiple access interference in the same way. So then I will show you some simulation results. This is in ultra-wideband.
For a second. So in this picture, these two pictures are more like multi-code CDMA.
Right.
Like you're going to multiplex. You're going to this plus really is combining all this.
Right. Right. So for the multi-code system, it may not transmit the same bits.
So Alex could ask you how do you implement this in UWB?
No, I have to say that this is a major advance compared to what I understood when I read this. So, I mean, this should have been in the thesis. Would have helped. I don't think there was these drawings were there.
Okay.
He's good at drawings, actually.
Well, some more of them should appear here because that was a
Okay.
confused reader by the time I got to that BER figure.
I agree, a lot of these figures should really go into
Okay.
So you call this multi-channel row?
Mm-hmm.
In the sense that your sequences are different or your pulse shapes are different.
The pulse shape are different. They are orthogonal.
They're all orthogonal.
Yeah. Let's assume that. Yeah.
So if we think of them as baseband pulses,
They
say
may.
they're orthogonal means that you need more and more bandwidth
Yeah.
to make the whole set orthogonal.
Yeah. They may not be baseband, or maybe.
Or even
So all in all, we want to create orthogonal channels. They maybe have a different band, but here we just say, oh, we use orthogonal pulse. Yeah, that's one way to achieve the
You can say
multiple
something
channel.
about the proposal, right? You told me that last night. The DS sequence. DS
Yes,
proposal.
yes, I want to say that in the.
Say it now.
Okay.
He's asking the question.
Okay. So one thing for the ultra-wideband system is people want to, because you have a huge bandwidth, like over 7 gigahertz. So So people don't want to simultaneously use the whole bandwidth. Sometimes people split it into different bands, right? So like for the multi-band OFDM, that's the same thing. You divide it into different bands. Each band have 500 megahertz. So that's one property of ultra-wideband system, right? So for our case, we also need orthogonal channels. That maybe we can use those different bands. So that's, but here we, in this case, we use pulse to just represent the orthogonal channels.
But it's also the other proposal also uses two bands, right?
Yeah, for the direct sequence one, they use two band, higher band and lower band.
To
Yeah,
avoid the 5
try to avoid the 5 gigahertz narrow band interference.
So each one of them they use sequences. So this would be an extension to multiple bands relative to.
So okay, so this picture now, I'm still confused.
Mm-hmm.
The yellow one and the yellow box labeled 2 are different bits?
The same information bits will be spread on all the channels.
Each channel.
Yeah.
It's like MC-CDMA. MC-CDMA is exactly this one.
So,
Well, you use different bits on different.
No, MC-CDMA.
no, that depends. They have some identity carriers or not. So they sometimes use some carriers to carry the same information bits. Sometimes they not. That's
There
the
are three variants of MC something, and
Right.
one of them is the one
Yeah.
that I think was established to be called MC-CDMA. It has this same bit on each.
Ah, okay.
yeah.
But there
But-
are 3 or 4 variants.
Right. But basically, for the multi-code system, they usually like carry different bits.
So if you do this, the self-interference in
Mhm.
the rate receiver is gone.
Right.
It depends on the rate, right?
And now
Yeah.
you increase the bandwidths,
Mm-hmm.
you double the bandwidth to do this, you also increase the number of paths, you did all kinds of stuff by doing that. You change the channel, basically.
But then
Mhm.
he uses the sequences too.
Now, but
So-
Larry's comment was, to do this, you need more bandwidth, clearly. But then when you put more bandwidth, you're changing the channel, so your channel has more multipath.
Mm-hmm.
So if this
So I wonder if you're winning at the end or losing.
Well, the good thing is this is kind of can cancel the multipath interference.
Because he cannot with less channels he cannot have a zero correlation zone. Now he
Right. He can have a zero correlation zone. That he can have anyway with a single channel. What he cannot have is the absolute
Right.
zero correlation.
Right.
that he
Right.
can carry with
Right.
this.
Right.
So the same bit is multiplied on each of these sequences, and then you sum all the sequences together, right?
Right.
Isn't that the same thing as if you have the bit times a composition of the addition of all these sequences into one extremely complicated signature?
it is.
Yeah, it is. We will talk about that.
It's like multiplying the matrix, right? And summing the columns.
Okay.
But,
All right. So
but
it is
they're all
that.
on orthogonal channels. So you're really sending a 2D picture over the web.
Okay. All right. Yeah. You just think about you saying
Yeah.
you decompose what the.
So this is the simulation results. Let's say we have the chip duration, which is 0.3 nanoseconds. So if we transmit, this is a single user. We only have one user in a multipath environment. So this user may use a ePato perfect ternary sequence with this length 21. Then that means it has the data rate like this. It may also use an M sequence with the sequence length like 15. This is the data rate. Or also, you can use two orthogonal channels, and each channel have a ternary complementary sequence. But you have this 15, length 15. So you have the same data rate because the same information bit carried by those two sequences, right? So you have the same data rate. So we can see that for this one, since we have two channels, all this have only one channel, but we do have we have the same data rate, but we have better performance.
So the perfect ternary don't give you as good performance
Mhm.
because they are perfect.
Only in periodic, right?
But the aperiodic would have the side lobe
Right,
where you get the self-interference.
right, correct.
But maybe, you know, with the zero zone, okay, where you don't need the two channels,
Mm-hmm.
who knows what you get, right?
For the zero,
For those ternary codes that have the zero correlation zone,
mm-hmm.
and you don't need the two orthogonal channels for that, right?
Yes, that's just one sequence.
It's just
Yeah.
one sequence.
One-dimensional
How
sequence.
do they perform?
Yeah, that's just the one. So here we don't. Yeah, I will show you some.
Do you understand this question?
Yeah.
What was the question?
His question is for the zero correlation zone sequence, what's the performance like that? So that's the thing we will talk about in the second topic. Yeah. Actually, I don't think we have some slides there because here we simply look at some typical sequence like M or those. So we have 4 users. So for each user, we assign complementary set. And any 2 sets are mutually orthogonal. So here, we use ternary mutually orthogonal complementary sets with the size 8 by 8. So this one may have a data rate like this. And we need 8 orthogonal channels. Then you may also use, like 4 users, each user use traditional sequence, that's one-dimensional. You only have 1 channel, that's enough. But you use a Go-like sequence with length 63. Because you have a long length, then your data rate is kind of low. So compare with these 2, actually they have almost the same performance. But this one gives you a high data rate. The trade-off is you have to have more orthogonal channels.
But if you take 52 and you multiply it by 8 channels, don't you get the state 400?
Yes, this one multiply this and this one multiply, they should be equal. But the problem is only the complementary sets can give you this. If you have other 2-dimensional sequences don't have the perfect ideal correlation properties, then you may have worse performance.
If you look at the bandwidth required for each of those 2 cases, doesn't your spectral efficiency come out pretty much the same? It is for the. I'll ask it another way. Do you need 8 times as much bandwidth for the complementary sets?
Yes, I need that.
But why do you say that one is? Show us the. So the question is, why do you write 52 megabits per second for Go-like versus 470 for the ternary if you're not using the same bandwidth? Like if you normalize them to the same bandwidth, what would be the rate?
No, the thing is for this one, you transmit the pulse, and you have orthogonal pulse, and you transmit them. And you have the length 8, then you will have the data rate like this.
What is the bandwidth you use for the first line, and what is the bandwidth you use for the second?
Well, yeah, here we have some assumption on the pulse. Yeah, that's the thing. This is the chip duration, and we assume all the pulse they may have this duration, but they are orthogonal.
But then you use orthogonal channels, right?
Yeah.
So your bandwidth is 8 times larger. So if you fix the same bandwidth size, then you would have the same rate.
So what's the advantage if you go to the next chart again? Why wouldn't I use the gold-like sequences? They have the same performance from what I understand versus the ternary and so forth.
Well, the thing is, if the sequence they don't have the complementarity, then this channel then you will have a lot of multipath copies. So if you select any kind of sequence, then actually this one cannot be cancelled. You may involve more multipath interference.
Gold-like sequences still have the same performance. So why?
You're showing that the gold sequences are showing the same performance.
Yes, yes. The gold-like sequence, they have the same performance because you have a very, very long length, so which can let you suffer from the intersymbol interference, less intersymbol interference. Here you select the short sequence. Basically, you may have more intersymbol interference.
So
that's
is your point that if you do gold-like sequences, you would have to reduce the pulse by 8 times? That's your point.
If
and that
you
maybe is too small, you cannot maybe handle that. But then it's easier to generate pulses on 8 different bands. And
well, yeah, yeah, that's another, yeah.
Is that the point?
Yeah.
You know, if you're buying jewelry, you would be very suspicious of a gold-like sequence. Gold-like bracelets, and it's
well.
Are you going to go for the ternary
it's a product at the dollar. So the question is, did you somewhere have a definition of what you mean by gold-like versus, is it some kind of a generalization of gold sequence?
Yes, because gold sequence cannot exist with like 4 to something. So basically from M sequence, you can derive the gold sequence. But for gold sequence, it doesn't exist with some particular length. But you can find something which is similar to the gold sequence. Then people call it gold-like sequence.
So that's a term people use.
Yeah. And it also has good cross-correlation and autocorrelation properties. That's typical sequence people use.
I still think this comparison is not clear because we don't know what are the bandwidths associated with each.
Okay.
There is something missing here that. But maybe we should.
Okay. So the problem to deploy this kind of system is, since you transmit the whole thing, you sum them and transmit, then you may have a high peak-to-average power ratio. That's similar to a multi-carrier system. So we derive an upper bound on the peak-to-average power ratio of the system if you use this complementary sets. This is bounded by, this number is just some system-related constant, like the chip duration, pulse, amplitude, like that. But basically, you will see this term. So let's say use SA to represent this. This SA actually, you sum the magnitude of all these side lobes. So you have all the column sequences. For each column sequence, you have a correlation. Then you sum the magnitude of the side lobes. You find the maximum one. Then that will bound the peak-to-average power ratio. So the thing is, if we can design the column sequences with very, very small SA, that means if you apply this sequence to the system, you may have a small peak-to-average power ratio problem. So we do have some method to construct ternary complementary sets. So we based on something we call companion pair that I will discuss in the next slides. But anyway, from this one, we can always construct ternary complementary sets. Here, I just do something like, this is the PAPR bound of the complementary set that use our way construct. And you may also random generalize some complementary sets. Then our proposed complementary sets do have some PAPR reduction. So now, before we go through our construction method.
Go back for a second. In order to construct that diagram, do you have to make assumptions about what the pulse shapes are?
Here the pulse, we don't have any pulse shape for that. because only the amplitude that may, yeah.
Sure. Do you have the equations? Is it in the previous slide? Lambda sort of
Yeah,
is
lambda, I didn't expand them.
So
This
it's
lambda
a
may,
constant and multiplies. It doesn't, you assume same pulse for both systems, so it's going to just change the constant. So relative,
Yeah, okay.
relative shape will be the same. That's his argument.
But if you're using, let's say, a two-dimensional signal, you have a different pulse for each sequence, right?
yes, if your pulse different, that really may affect the lambda, but now this is a bound, so you can always get the peak of your pulse. So that's the thing we get into this lambda, yeah. Because this is just a bound, not the, yeah.
For the complementary sets, we understand with the two sets and the properties of the aperiodic correlation
Okay.
function. Is there any advantage to have now 8 instead of 2? I mean, 2 is 2 channels. That's better than
Yeah.
8 channels.
Yeah, because if you have only like complementary pair, right? So for this complementary pair, actually you can only find one of its mate. So you can only assign to 2 users because you only have 2 sequences in this set. If you want to assign a lot of mutually orthogonal complementary sets to a lot of users, you have to increase the size of this one. Then you can construct more mutually orthogonal complementary
So
sets.
what you are telling me is that if I want to use this approach with 8 users, I actually need 64 channels.
If you want 8 users, then you may need 8 channels. For each channel, you have 8 by 8 complementary sets.
So each
Yeah.
channel is sort of but it's really 64 channels if I compare it to a one-dimensional type sequence.
Well, that depends on where you start from the construction. Because just now I didn't show you the...
What's the dimensionality of the signal?
Yeah.
It's going to be 64, I think. Right?
Yeah, you can be... Okay, yeah, you can say that, yeah. Here,
How many orthogonal pulses do you need?
for each channel, you need an orthogonal pulse.
How many channels in what he asked?
Depends on...
Is it 8 or 64?
Depends
Or
on...
8 users?
That really depends on where you start from, because this is a recursive method to construct complementary sets.
Well, let's assume you have a design. You have some
Yes.
design.
Yes,
You want to support 8 users.
right. So now here, this is a complementary pair, and we get its mate. That's 2 matrix. So based on some matrix operations, you can get 4 complementary sets with 4 channels, 4 orthogonal channels.
And how many users do you support?
So you can support 4 users.
So if you have 8 users, you can form
8
channels.
8 channels, yeah.
Not 64.
But also you can get the...
So is it 64 or 8? That's the big difference.
Yeah, for 8 users, 8 channel is necessary. Yeah.
And what's the size of the zero correlation?
No, this is zero. This is not zero correlation. This is ideal correlation you will have. Yeah. So now, the thing is, we want to construct complementary sets with really good correlation properties. The column sequence here, all of them has some good correlation properties. So the problem is, if for a given complementary set of a given size, then what kind of assay that you can achieve? That's the thing we want to look at, because the minimal achievable column correlation constraint may give you a minimal PAPR bound. And once you know that what the minimum SA is, then how you construct complementary sets can achieve that. And the third thing is, in general, here we look at PAPR, we may look at SA, but maybe we also look at some other criteria, because for the sequence you may have different criteria to determine the sequence, to determine the good or not of a sequence. So we may want to find some general construction method to construct a complementary set whose column sequences satisfy some correlation constraint. So here I show you a big picture that what we do. So we start from something called a companion pair that I will talk about in details in the next slides. So from these two sequences, based on some sequence operations, we can get a complementary set. And then from this complementary set, based on some matrix operations, we can always get a mutually orthogonal complementary sets. The good thing is we can relate the column correlation constraint in this mutually orthogonal complementary sets to the autocorrelation of that two sequences. So which means if you want to construct complementary sets with some correlation property, then you can always find that two sequences with some corresponding properties. Then I can guarantee from here you can construct something here. So we have a series, lemmas or series, to talk about this. Then let's look at what's the companion pair. So this is something that we construct. We found that if we have two sequences, they have some structure called, we call it cause. And this is also others call this structure as cause. So which means if you pick up any two columns, not any two. So if you have, so this companion pair actually have, if it has length n, then it must have n over 2 cos here. So like this one actually has this cos structure. So this sequence actually have a lot of cos. If that two sequences has this structure, then based on our method, we can guarantee we can construct something with correlation properties. One thing I want to mention is people doing research on the cause, that's a long time ago, they found that the binary Golay pair, that's the binary complementary pair, they have some nested cause, which means the cause structure, they have some positions, you have to fit in that position. But in our companion pair, actually those cores you can have arbitrary position. So in this way, we can say the binary Golay pair is just a special case of our companion pair.
So I remember when I first encountered quad in the thesis, I wasn't sure what it was, and then I couldn't find the definition.
Mm-hmm.
Is this the definition of a quad that, like those, the pair of 2 by 2 matrices that that have this kind of anti-symmetry? That what is defines?
This is what we define, because previously people look at binary sequence. They have some code that don't have this conjugate. But we just apply some conjugate and apply them to the complex value sequence.
But is there a definition of a complex quad?
No, there is not.
Sure?
Yeah, no.
So this is your definition of the...
For the complex value cause.
And you're going to apply that, like when you say that, so you have these length n sequences, right, of the binary Golay pairs, for example, and then you say they're formed by n over 2
nested.
And is that obvious?
Yeah, this nested, which means if it's a complementary pair, then all the cores, they have some, you have to fit the cores into some positions. But in our case, for our companion pair, you can have the cores in arbitrary positions. But if it is a cause, then that's the companion pair.
because when he says nested, I guess he means that just any two columns, or that there always appears a column that controls.
So you take any two columns and then it does this?
No,
Not-
if you find a column,
not
that
any.
its other pair.
If you have one column, there should be some other columns that have this structure. That let you to be a chord. But the position of that one can be arbitrary in our case. But for the companion pair, if you have one in this position, that's the other part of the chord must be in some place. Yeah.
I don't know why that's nested.
So we may not only look at SA, we may also look at lambda A, which is the maximum magnitude of these side lobes. So we may look at general correlation constraint. We may also look at the column sequence are also glide sequence, are also complementary sequence, because we know that the complementary sequence has the PAPR less or equal to 2. So we may also construct something with glide sequence in column. So that's what the correlation constraint that we look at.
But, I want to be sure I understand that. So you're saying for an arbitrary number of rows, your peak to average power ratio is less than 2?
For columns,
Yeah.
this is a complementary set. So each row are complementary sequence, right?
Yeah, right.
But we can have some method to let the columns also to be complementary sequence.
Right.
And people have some results. If it's a complementary pair, one of the complementary pair, then the PAPR of that sequence is less or equal to 2.
So for any complementary sequence that has nice good PAPR.
Yeah.
So for every column, thinking of that as an instant in time, you look from one time slot to another,
Right.
from one column to another, to another.
Right.
Yeah.
And look at the peak and the average,
Yeah.
it's less than or equal to 2.
If it's a glide sequence.
Yeah, right.
Yeah.
Okay.
Yeah.
It's a really nice property shown
Yeah, it
by
is.
some really theoretical people.
It is a nice
Like
one.
mathematicians, actually.
Things which I
Right, she, Juliana's, they use a jadwal.
How did you know that?
I did a huge rough on that before I started working.
Okay.
So the problem here is, let's say we want to achieve some column correlation constraint here. Then which means we want to find some companion pair has some autocorrelation constraint for each sequence. And those two sequences have some cause structure. So what we do is we can try to do the exhaustive computer search to find those companion sequence. We want them has very, very, very small, or we say minimum correlation constraint. Then, which means we can, from that, we can construct some complementary sets with optimum column correlation constraint. So for the short length sequence, we can always do the exhaustive computer search. So here what we do is, let's say for the length 26, for this one, if we want to construct a binary complementary set, then what we do is we try to find the binary sequence with constraint SA or lambda A with the minimum of this. That's the best binary sequence, which has the minimum autocorrelation constraint. But we can get some of them. From those, we found that we can always find our companion pair in that set. So which means our companion pair can always achieve the minimum autocorrelation constraint. So that means our method can leads to the optimum binary complementary sets, at least up to length 28. Because for higher lengths, I have some trouble to do exhaustive search. For this 28, which take me like 2 or 3 days. So for the exhaustive search, basically we cannot deal with long-length sequence. But this table shows that if you pick up the companion pair here, use our construction method, you can construct the optimum complementary set. And this is something for the ternary sequence. From this ternary companion pair, you can always construct optimum ternary complementary sets. But for the long-length sequence, the problem is something, so you cannot do the exhaustive search. What we do is we try to find some bound to estimate for the long sequence what kind of correlation constraint that you may achieve. So this is a very common problem in the sequence society. People always do something like, for traditional sequence, for a given length, then can you get the autocorrelation property like this? So people always ask this kind of question. So for this example, yes, this is Bach sequence can achieve this. But Bach sequence only exists for this length. For long length, people not sure what's going on there because you cannot do the exhaustive search. So this problem is very hard. In our case, the problem is even hard because we are not only deal with a single sequence, we deal with a companion pair. Both of them should have some correlation constraint, but they also need to have some cause properties. So what we do is we get some, we use some workaround way. We use two interleave, two short length sequence to get a companion pair. We have some bound on the autocorrelation constraint. And we search for that other two AD sequence to get the bound of the long length companion pair. So that's what we do. And this thing give you some feeling like if you construct a big complementary set with the column sequence length as this, then I say, well, if you say, oh, you want to achieve the lambda A to be 24 or larger, then I can say, yeah, you can do that. But as for 20 or whatever, I'm not quite sure. It may be or maybe not. But this gives you some sufficient conditions. So we also using some search algorithm for the long length sequence to find those AD sequence which may help you construct companion pair needs to complementary sets with good correlation property. So this is a whole story. We study ternary complementary sets. We study its construction, its property. We apply them to the multi-channel UWB system. We derive the upper bound, and we found that we have to deal with the column sequence. So we exhaustive search for the optimum columns, optimum companion pair, and we also for long length sequence we also provide some good companion pair. So our contribution is we have this general method, companion pair based construction method, which can deal with, in general, deal with complex valued complementary sets with good correlation properties. Well, our first topic is the two-dimensional sequence. For the second topic is one-dimensional sequence. For one-dimensional sequence, you cannot achieve the ideal correlation property. So we want to do is we get a zero correlation zone in the sequence correlation functions. So zero correlation zone also has some relatively short history. In 1999, people look at the binary periodic zero correlation zone sequence, which means the zero correlation zone is in the periodic correlation. And also Char look at ternary periodic zero correlation zone. What we do is we look at ternary ZCZ, but this ZCZ actually both in a periodic and a periodic autocorrelation. So which means this kind of sequence may give you better performance. So this is the conventional. But yeah, another contribution is in our work is previously people only look at the zero correlation zone sequence set. They may have the same sequence length, but we extend this to a tree structure. the sequence may have different sequence lengths. So this may be good for the ultra-wideband system because ultra-wideband system may deal with different data rate applications. Sometimes you want a voice, sometimes you want a data or multimedia. So if you select the short length sequence, actually you can achieve the higher data rate. So this is the orthogonal variable spreading factor codes. So which means if you look at the codes at the same layer, they are orthogonal to each other. The orthogonal means inner product. If you look at the codes at different layer, if this one is not generated by this one, that means this one is not the leaf of this one, then they are also orthogonal. Here orthogonal means you periodically extend this and do the inner products. So this is good properties for the OVSF codes. Any codes as long as they are not parent or child pair, you can assign to users and you have the orthogonal code. So this is conventional OVSF code, which generated based on Welch code. But in our case, we from ternary complementary pair, we can generate ternary OVSF codes. But these OVSF codes with a zero correlation zone in both periodic and aperiodic correlation functions. So one thing I want to emphasize is when you assign those codes to the users, you have to satisfy the craft inequality. That's the prefix constraint. Like here, let's say we have 4 users. We can assign the second layer code to 4 users. Then actually you have already make this value to be 1. So which means you cannot assign any codes to any users. And in this case, if you start from the ternary companion pair of length n, then the zero correlation zone of the whole tree structure will also be n. So this shows you from this ternary complementary pair, we can construct the whole structure. If we pick up the first layer code, it do have a zero correlation zone. The length of the zero correlation zone is equal to the length of ternary complementary pair. Well, we may apply this kind of sequence to a quasi-synchronous direct sequence CDMA system.
So you have a bigger output then, right? And you have 3 symbols instead of 2 symbols. So like compared to regular OVSF, OVSF is the whole tree is derived as, it's a symbol construction with prefixes, right? And
Yeah.
And they're binary symbols.
Yeah.
A binary tree.
Right.
But you have 3 symbols, right? Or are you not using?
Are
you doing binary symbols?
Also using binary symbols. Yeah. This is also the construction method is the same. The only thing is I don't use the Welch code. I use ternary complementary pair. Then you can have zero correlation. So it's still the binary tree.
When you say symbols, you mean
So it is his. So
each sequence is ternary.
So he starts with this ternary complementary pair, and then what he is calling OVSF is the 2 nodes that are descendants of a node have the same prefix in terms of whatever prior construction, and then they're just modulating this pair, like to construct the.
Yeah, this is still a binary tree. So, but each sequence is ternary sequence.
So that's the relationship. Yeah.
This is still the prefix. It's the same thing as the previous one.
There's no difference.
No difference.
Just the seed.
Just the seed sequence are different. Yeah.
Not binary.
Yeah.
But if you change the seed sequence to be this, you may have zero correlation zone. That's the thing. But also the trade-off is the sequence length also increased compared to the Welch code based. So this kind of sequence. Okay.
So you say these things as though. But the trade-off is that the sequence
length at the same layer, you may have a long length for this ternary sequence.
And that's because you did the construction using these complementary pairs.
And also I insert zeros between them, so that's why I increase the length.
Okay. So the price you pay essentially essentially for gaining zero correlation, so there's
Right.
bandwidth expansion.
Right. So,
Did you somewhere
okay.
say what the price, like sort of evaluate that, what that bandwidth expansion is?
No, we didn't do that.
That's sort
Okay.
of the key thing,
Okay.
right?
The trade-offs. Okay.
Why, how.
Okay. Okay.
Or at least when you also do this bandwidth expansion, right?
Mhm.
Then if you build an actual transmission system, right, you derive some benefits for that, right? That you have.
Mm-hmm.
If you go through some multipath channel, presumably your system will work better than the ordinary OVSF which
Yeah.
Was just binary and which now has.
Yeah, but when we do the comparison, actually we compile those sequences, like the originally Welch code-based sequence and our Ternary sequence, they have almost the same sequence length, comparable sequence length. So when we compare the performance.
Okay.
Yeah.
So then you're saying, there really isn't much of a bandwidth expansion. Like they have the same sequence length.
Mm-hmm.
Is you saying they?
Yeah, the zero correlation zone has better performance. Yeah, you don't have the same sequence length. But that depends on the channel. I mean, because this is zero correlation zone. If all the multipaths fall into your zero correlation zone, you're very good. But if something is outside, maybe depends on the channel and your zero correlation zone length.
Well, but usually in most physical situations, right, you can get some sense of like the sort of the maximum delay, right?
Yeah. I can always construct a zero correlation zone like
With respect
larger
to
than
the
that, yeah.
maximum path
Yeah.
delay,
Yes.
right? And then so it sounds like what you're saying is to use this technique. You would say, we're doing this in cellular. I ought to look at paths that are a couple kilometers of delay. This I guess it's all ultra-wideband, but in some of the math in this case doesn't seem to matter. It's ultra-wideband. It seems
not necessarily ultra-wideband. Yeah. Okay. So we would apply this kind of zero correlation zone OVSF codes to a quasi-synchronous CDMA system. So we have a base station and several users. Let's say they have the GPS, so they know the relative distance, so they can compensate those distance difference. So this can achieve the synchronization even in uplink. But the problem, you may have some synchronization errors. Let's assume that synchronization errors, or we call relative time delay, within this range. So if we can construct a zero correlation zone larger than this range, then actually you still have orthogonal, you still can keep the orthogonality. So what we really look at is the code assignment issues. For here, we have 4 users. So you may assign this code to 4 users. This code may have sequence length, let's say 2n. So you may have some other way to assign the codes, like the green one, to the users. Some of them may have longer length, some of them may have the short length. Then maybe they may have different throughput. So which way that we will choose to maximize the overall aggregate throughput of the system, that's what we will look at in this research. So this is the system setup. So let's say relative time delay fall into the zero correlation zone. And this is the BPS case system. This is a package-based encoded system. So you transmit, so J bits will be in a packet you transmit out. If one bit error, one or more bits, you get some error, then you will retransmit the whole package. So this is the throughput will be. So this throughput function is a function of the layer number k. So the k number k also related to the sequence length, because at different layer, the sequence may have different lengths. So this is a function of sequence length and also the signal to interference and noise ratio of the user. So let's look at this curve. This actually is a throughput function when you fix the layer K to be 1. When you have different signal to noise ratio, then you may have different throughput. Then for the second layer, let's say this blue one, you also have some curve. But the thing is, since this layer you may have longer lengths, so if we fix the chip energy, then actually this one, this one may have some difference with the previous one. So we may have a set of curves, that's throughput functions, each curve corresponding to one layer codes. So let's say when we have 4 users, we may do some non-adaptive case. We just assign that 4 codes to the users, that's it. But somehow we may know the gamma of the users. Then we may find some adaptive way. For example, we may assign the codes in this way. Or we may assign the codes in this way. So of course, this one may give you better or aggregate throughput. So our research is doing some research code assignment scheme to maximize the throughput. So this is the general problem statement. You have a lot of curves. And since you assign the code to the users, you have to satisfy the graphing inequality. So that's the constraint. But what we want to is maximize the sum of the y-axis of all these users.
So what is the, like I gather that the x-axis is a SNR,
Yes.
right? And
Yes.
the y
Y is throughput. So for this user, if you select a different layer code, you may have different throughput. However, if you select the first layer code, actually you take a cost 1/2 here. And if you select the second layer code, you only take a cost 1/4. But the overall cost should be less or equal to 1. So for all these M users, you try to select one point from this y-axis. But you take some cost. You want to maximize the overall throughput.
What would you do if the sum exceeded that bound? Then what would be the next step?
Then you have to select the lower layer code to give share some code to other users. So we have to assign those code to these M users.
You law for this is how much you pay. You cannot deal with it much.
Yeah, right.
Or you will lose the orthogonality. That's the thing, yeah.
Is this any different if you want?
I'm trying to think. I think I may have solved this problem.
Yes, you have, but for certain throughput forms. He will talk about that later.
So he knows whatever kind of thing I have to solve.
Yeah, he'll have
Oh,
your
good.
reference.
Okay, he can remind me.
Yeah. So this is similar to a binary knapsack problem. It's kind of a hiker fill up his knapsack with some capacity constraint, right? You have a lot of objects. Each has a comfort and also have a volume. So you put them into a bag, but you want to maximize your comfort, but subject to the overall volume. That's the thing. So, but our problem is somehow even harder because here we have infinite code because that tree can extend to infinite numbers. And also, it's kind of different because this user may select objects here, and this user select objects here, but they have some costs like that. So we deal with different type of throughput. Okay.
The one that you just skipped over. I just want to look at.
Okay.
Okay. I'm looking at the bottom equation.
Okay.
Yeah. Right.
M is the number of users. K is the layer number.
Okay.
Yeah.
That's the problem I was referring to. How do you do that?
Mm.
That's the constraint. You
Yeah,
have to
right.
ensure that
Right.
it's satisfied.
So we look at all these throughput functions, this one is actually the one KEMA take. And we may look something different. So,
okay, so this is the one I have worked on.
yeah. So,
It's vaguely familiar.
so we have some tools that can help us to do the code assignment. This one we call it self-maximization. We should deal with a single user. Let's say you have a single user. But this user, because other users may already take some layer code, so this user may have some constraint on the code layer. For example, let's say this user, you cannot take the layer which is lower than Ka. You have to take the higher layer codes. But you have some gamma. You want to maximize your throughput. For example, like here, the user have a gamma here, right? So the Ka, let's say Ka is equal to 1. Then which means that user cannot take the K equal to 1, right? Because your K should be larger than Ka equal to 1. So you have to take the second layer or third layer or fourth layer code. But the good thing is for this user, you're not necessary to take this one. Because even if you take the first layer, you may have a worse throughput. So this user, if you have a gamma here, you will always take the second layer codes.
D, it's K equal 2 because you have equality there. This is for K equal 2.
No, this is also work for Ka equal to 1. Because you want to maximize your throughput. Okay. So this is the one that you can maximize. Yeah. So if K equal to 3, well, then which means you cannot take the second layer code because 2 cannot be larger than 3. So you have to lower your layer to 3. So this is something we call self-maximization for a single user. So based on this self-maximization, we can do some initial code assignment. This initial code assignment try to satisfy the user with the largest SINR. For example, we have M users, they have gamma here. We first assign code for the first user. This user can always take whatever he wants. So he will take this one. That means he will do the self-maximization based on this. But for the second user, because this one already take this, if second user take this one, which means you already have the cost equal to 1. So that user cannot take the first layer code. You have to take the lower layer. So you also do the self-maximization in this way. Then you may have a code assignment for the second user like this. So keep on doing that. We can get all the users assign all the users some code. So this is we call initial code assignment. But the problem is whether the initial code assignment is optimum or not. So for example, like in this case, initial code assignment may not be optimum.
What do you mean by optimal?
Optimum, which means you can maximum throughput.
What if you throw fairness in and say, well, you don't want to cheat the little guys out of anything.
Mm-hmm.
You could fill up all the codes with just the first 2 users, and everybody else gets nothing.
Yeah, so
the other end it worked out.
Yeah, so we assume in a battlefield, every user should contact with the commander. They cannot lost their right. That's something. Yeah. So the initial code assignment may not be optimum. In this case, let's say you take the yellow codes to 4 users, they may have the throughput like this. But if you change, this is the one that the initial code assignment will give you. But if you change it to be the second layer codes, so this one, the first, no, I'm sorry, this one should be also in the second layer. So for the first layer code, you compromise a little bit about your throughput, but for other users, you may have a huge increase in the throughput. So which means for this case, initial code assignment is not optimum. But for KEMA's case, for this type 1 case, it's optimum. So in general, it's not, but in this case, it is. So we may look at in this case, whether we can find some optimum solutions. Okay.
I'm trying to see what the essential difference is between these two. It's just
Okay.
it's the shape of the curve. One is smooth and one is step.
Yeah.
Step-like.
Yeah.
That makes the whole difference.
Yeah.
You should have, can you explain it? Maybe.
Yeah. So that depends on where your gamma is. That may affect you select different layer codes. Yeah. If you gamma in this way, then actually this one also, or you take, you maximize yourself, you maximize the throughput of yourself, but actually you take a lot of cost, like 1/2. But you are greedy because we always satisfy the first user. But for other two users, because they only have a small, their signal to noise ratio is just a little bit less than that one. But they have to choose some very bad sequence.
Did
So
you understand the essential difference? I mean, see, the thing is that these curves that are step functions, there's a dyadic, right? There's a dyadic relationship between them, right? So you really earn a lot if you go to the next one.
Right.
But if you have a smooth curve, you go by a little bit, and then that might not be worth it.
Yep.
So, and that is more a realistic sort of shape of a throughput versus the dyadic.
So your curves you got were by, it's not, like you don't have a coded system here, are you just doing sort of a
this uncoded.
uncoded any
To get the curve, but if you ask Rohank, he'll give you very similar curves with some.
Yeah, but I look at Rohank's thesis and I say the abstraction of his thesis is to draw those straight dotted lines.
For really long codes.
Yeah.
If you decide to do shorter codes, then
True.
So we have
How
some.
do you feel like, that's, as you said, right, you're using a lot of bandwidth and you're,
Mhm.
you're doing a lot of bad bits being transmitted.
right, that's what the solution of the self-maximization would be. That's the point that he's making. Or he should talk the solution.
So based on the initial code assignment and the self-maximization, and we also have some group maximization definition, but I will not go through in the details. We can get the optimum code assignment. So this shows you some system setup. We compare the initial assignment, optimum assignment, and non-adaptive assignment. So this is the battlefield. We have like 4 users, 1 base station. And these 4 users, they can move into this, but within this range. So for each position, they may have different relative distance to the commander. So they may have different signal to noise ratio. For each position, we may have some code assignment, but we may change the position of these 4 users. We over 1,000 positions, and for each position we get aggregate throughput, and we average them, get the aggregate throughput here. So this EC is the chip energy. For each user, you always fix the chip energy. If the chip energy goes to infinity, very high, then actually everybody will work in this place, because you will have a very high gamma, because your EC very high. So this is same thing like Kema's case. So if you have a high EC and 0, then basically everything achieved the same thing. And the initial and optimum, they're the same. Well, if at very low EC, they're also almost the same. You don't have any throughput. But one thing is, this group of curves, actually for m equal to 4, which means we have 4 users. So this is the non-adaptive case. This is the initial and optimum case. So initial and optimum case can achieve the throughput gain. But the initial case and the optimum case, they have almost the same average aggregate throughput. That's because this case may not always happen if your gamma, spread it along this. So this bad case actually have been averaged out. So that's why here they may have almost the same performance. But if you, in the simulation, if you really look at the instantaneous gain, then you may catch that bad case. You may find that for the instantaneous gain, the initial code assignment, the optimum code assignment may have 20 megabits than the initial code assignment. So it depends on whether you want to achieve the instantaneous gain or you want to achieve the average gain. If just in average, maybe you can just simply use initial code assignment because that's simple. You don't need a lot of time to do the code assignment. But for the optimum one, you need to spend a lot of time to assign the code. Well, this finished the second topic. We look at the zero correlations on OVSF code. We apply them to the quasi-synchronous UWB system, and we propose some method to maximize the aggregate throughput. The third topic is a small topic, just 5 minutes, then I will finish this. So for the previous one, we try to design sequence with good correlation property. That means we may not have any channel information. So what we do is try to design sequence, the best sequence, the ideal correlation property like that. But if you have some channel information, then combined with the channel information, maybe not some good correlation, maybe some special correlation functions may help you, but that may not be good, may not be the ideal correlation. So in this case, let's say in the ultra-wideband system, we know the sign of the first LC pass, or we say first LC strongest pass. Then we evaluate the sign. If we know that sign, somehow we have some criteria to exhaustive search for a ternary sequence which can maximize that criteria. Then if we know the sign like that, then we transmit the corresponding beamforming sequence. We call beamforming sequence. Then you can simply make your receiver as a correlator receiver. Then the result is the energy of that first strongest LC pass, the energy of those paths will coherently combine. So which kind of like you do something like at the transmit site to do some pre-rake stuff, but you transmit the sequence. So at the end, you will achieve, using a correlator, achieve almost the same performance as a rake receiver. This is the criteria that we use. Basically, we calculate the energy of the multipath if you know the sign and you know a sequence. We use this criteria to exhaustive search for short-length ternary beamforming sequence. So this is the simulation result. This beamforming 4, which means we know the four signs. Then we, based on that 4 signs, we find we exhaustive search for the best beamforming sequence, and we transmit this. This is the curve for it. So this we only at the receiver we only use a correlator receiver, correlate to the first pass. Then that's it. But for this can achieve the same performance with M sequence of the same length, but you will use a MRC rake receiver. So this means if you use this beamforming sequence, if you know the channel information, then you can simplify your receiver. So this concludes our research. So we look at both 2-dimensional sequence, 1-dimensional sequence. And 2-dimensional sequence is kind of has problem like PAPR. So we find some way to reduce that. For the y-dimensional sequence, we construct something which has 0 correlation zone. And we have some throughput maximization code assignment scheme. And also we look at beamforming sequence, which if you know some channel information, get some sequence with some special correlation properties to maximize the output of the correlator receiver. So some future work is in our complementary sets design. So the thing is we say we have designed some optimum complementary sets with some we verify that by some short length. But the thing is whether we can find some way to somehow show that our construction is always optimum for longer lengths, then that would be good, but that's very hard. Also, for search for good length sequence, we use simulated annealing algorithm, so that those algorithms can always be improved by set different parameters. So you can always you can always get some improved bound. Okay, so that's all for this presentation.